All right, welcome back, everybody. So this is video going over section 8.1. Take a look here at the homework. Start checking your answers. This is, I don't know whether you call this the front or the back. You call this the front. So this is the front. This is showing the LCD with the full number. You know, whatever you want to multiply in by, but that's like the LCD is 2 times 2 times 2 for number 1. So when you multiply in, you'd just be multiplying by the 2 on the top. That's why you get the 6. Here you wouldn't be multiplying, you'd cross cancel the entire thing. So leaving a 3, you'd cross the cancel to get a 4, you get a 12 there. Add the 12, divide by 3. Number 2, the LCD is just 2 because there's only denominators of 2. So you multiply in, cross cancels the 2 with an X. You multiply the full 2 in, you get the 1. 2 times 1 is 2. You cross cancel with the 2 to leave the 3. Subtract the 2, get an X equals 1. Number 13, the LCD is 14. Or sorry, number 3. The LCD is 14 or 2 times 7. Multiply it in, it cross cancels with the 7. You get the 2. 2 times 2 is 4. This cross cancels with the 7. Get a 2. Multiply in 2 times 1 is negative 2. The cross cancels the full 14, so it just leaves a 3 and solve your equation. Number 4 on the right side, again, that's a 2 times 2 times 2 if you want to treat it that way. Multiply it in, cross cancel with the full 8, get an X. Cross cancel 2, and one of the 2's get a 4 on top. Multiply in 1 times 4 is 4. It doesn't cross cancel anything on the right side. 6 times 8 is 48. Add the 4 to get a 52. And then here's 5 and 6. Number 5, the LCD is 12 or 2 times 2 times 3. This cross cancels with one of the 3's to leave a 2 times 2 or a 4. Times y is a 4y. This cross cancels here with just a 4 and leaving the 3 on top. So 1 times 3 is a 3. This cross cancels with the full 12 to get a 5. Add the, or subtract the 3 divide. Oh my gosh, you scared me.
Sorry.
Oh my gosh. It's 7:45 and then when you scared me. I'm still sleeping. Thanks. Oh my gosh. Freaking ninja.
I was going to say something and I was like,
No, I didn't. She was just there. Right? Who was that? What was it? Bella. Bella Cardin. Yeah, watch out for her. Holy chicken nuggets. Subtract the 3, divide by 4. Y equals 1/2. Number 6, the LCD is an 18 or 2 times 3 times 3. 2 times 3 times 3. That'll cancel one of the 3's to get a 2 times 3, which is a 6. Multiplied in with the 12, or 2 to get a 12. This cross cancels with a 9, just leaving a 2 left over. So 10 times 2, or sorry, 5 times 2 is 10. This cross cancels with a 6, so leaving just a 3 left over. 1 times 3 is 3, and just solve. Any questions on the front side? My opinion, the front side was a little bit more straightforward. The back was a little bit kind of weirder with the parentheses and whatnot. So go ahead and check the back here with 7 and 8. Yeah, like number 8 there. 7 really straightforward there, but number 8, because this is a sum divided by the full 3, you can treat it like, 4 plus m all over 3 is another way to write 1/3 times 4 plus m. That's right. That is right. 4 plus m all divided by 3. Another way to write that is 1/3 times 4 plus m. So to clear out that fraction, all you would need to do is multiply that whole thing by 3, right? But we're not going to do that. We're going to multiply the whole thing by 6 because that's my LCD, or 2 times 3. So when I multiply it by 6, that's going to cancel out the 2 times 3 here. That's going to cross cancel with the 3, leaving just the 2. So 2 and then 4 plus m. And then we multiply in here. If I want to think about it like this, 2 times 3, cross cancel with the 3. Now we have a 2 coming in, leaving an 8 plus 2m. And then obviously the 5 on the right side stays. Here's numbers 9 and 10. Same thing there with number 10. I could have treated number 10 like 1/2 4 minus k. That's one term, one whole chunk, right? So if I want to clear out this fraction, I know I need to, this is 2/5. I know the LCD is 2 times 5. So if I'm going to multiply this whole thing by 2 times 5, I'm just going to multiply this piece in here, cross cancel with the 2, leaving just the 5 coming in. 5 times 4 minus k. And then I do the same thing over here, cross canceling with the 5. 2 times 2 is 4. Okay? Another way to think about that is if I had done this, 4 minus k, all divided by 2 is equal to 2/5. That's an equivalent statement right there. And then I multiply with the 2 times 5, or the 10, cross cancel with the 2, leaving just the 5 times the numerator, 4 minus k. Cross cancel with the 5, leaving just the 2's in the numerator, you get a 4. And then it works out the exact same way. All right, and then here's 11 and 12. Those ones are pretty straightforward. Not more straightforward than other two are kind of in order. Okay. So again, I can't stress it enough. I've been hearing people say to me the last 2 days, "Well, I don't do it your way, but my way still works." It still works for numbers, right? It still works for numbers. Will it work when we get to rational functions? I don't know. I don't know what's going on in your head, right? If you follow my way will work when we get to rational functions. It is very convoluted when we're just talking about numbers. I get it. I am not trying to try to sway you to think about numerical fractions in any other sort of way. What I'm trying to get you to do is shift your thinking, learn it in a new way so that when we get to rational functions, it's easier for you in the long run, okay? So again, don't think that I'm trying to teach you some new way of adding and subtracting, multiplying, dividing fractions. No, your way works. Your way is good. Whatever's working in your head with numerical fractions is good. I'm just trying to teach you a new way, a new method of thinking that, this is kind of like a safe space with numerical fractions, right? You know how to do these things. So I'm trying to teach you new methods with this so that when we apply it to something a little bit difficult, that makes it a little bit easier, okay? So let's get to section 8.1. Let's get started within chapter 8. It's called variation functions. Variation functions, kind of like the introduction to rational functions. Variation functions. Variation functions. Now, I will tell you that you've learned some of this. Well, you should have learned some of this in Algebra 1. Whoa. You don't have to submit anything. The only thing I needed to submit was the homeworks. All right. So there's two types, well, I shouldn't say two types. Kind of like 3 types of variations that we're going to learn today, okay? The first type is called a direct variation. Now, in Algebra 1, you studied direct variation. I believe in this class, we studied direct variation as well, okay? In chapter 2, we studied many types of linear functions. One special type of linear function is called a direct variation. I know this is taught in Algebra 1 because I teach it in Algebra 1. A direct variation is a relationship between 2 variables where if I increase one, the other one will increase it with it, or if I decrease one, the other one will decrease with it. They go hand in hand. They vary directly, okay? That's a direct variation. A direct variation is a relationship between 2 variables, x and y, that can be written in the form y is equal to kx. Mathematically, you can write it in this form, where it's an equation y is equal to just k times x, where k can be any number. Y is equal to 3x is a direct variation. Y is equal to 5x is a direct variation. Y is equal to 10x is a direct variation. Y is equal to negative 3x is still a direct variation, okay? They vary directly. When one goes up, the other one goes up. When one goes down, the other one goes down. And that also means I could take y is equal to like 1/3 x. That's still a direct variation. Will you notice here that there's no plus or minus outside of the end? This is a linear function with basically no y-intercept, which means if there's a 0 y-intercept, what point is it always going to run through? The origin point. It will always run through the origin point. Always. A direct variation will always run through an origin point. Okay? That k has a unique name. It's called the constant of variation. The k is called the constant of variation. So this is what what a direct variation looks like. We talked about the 0 being the y-intercept. The k value ends up being the slope. The constant of variation ends up being the slope. So if I say y is equal to 5x, obviously m is 5, k is 5. The k value is the m value. Okay? The constant of variation is our k value, y is equal to k times x. Notice that it's multiplication. It should not be division. We should not be dividing by x. We should be multiplying by x. Y is equal to the constant times x. And how do we speak that? We say y varies directly with x. Okay? We're going to do a lot of some word problems within this section. And if you ever see the phrase varying directly, that means you know it's of this form. Y varies directly with x. So let's take a look here. Given y varies directly as x and y is 27 when x is 6, write and graph the direct variation function. Okay, so I'm given enough information to write out my equation. I know that this phrase, that given that y varies directly as x, that tells me that my final equation should be of this form. And y is equal to k times x, because if I use the phrase varying directly, I know it's got to be this equation, y is equal to k times x. Well, then the next phrase tells me basically an ordered pair. Y is 27 when x is 6. So basically, I know 6 comma 27 is on that line. When x is 6, y is 27. Y is 27 when x is 6. So what I can do here is I can solve for my k value. I can say, well, if y is 27 when x is 6, I know that equation is true. So I just divide by 6 over to the other side. So we would take out a common factor of 3. That's 9 halves is k. If you wanted to give me 4.5 there, that'd be fine too. And for our purposes right now, I'm okay with the decimal. Later on, I will not be. Right, 27 over 6, 4.5. All right, so y is equal to 4.5x, or 9 halves x. Y is equal to 9 over 2x. I guess I'll write it as a fraction as well. I like it as a fraction because isn't that slope? Is the k value slope as well? We know it's always going to run through the origin point because there is no y-intercept. So I can make one point there. And then, you know, I could use this 6 comma 27, but obviously 6 comma 27 is not on our line, or not on our graph. So I'm just going to use the slope of 9 halves, rise 9, run 2, or down 9, left 2, to graph my line. There's my direct variation. Ooh, I kind of missed my origin, but that's okay. You get the idea. So a direct variation is a straight line function. A direct variation is a linear function, okay? Direct variation is a linear function. It's not going to be true for inverse once we get there. All right, so how does this apply to word problems? Well, the perimeter of a regular dodecagon varies directly as the sideline to x. And p is 18 when s is 1.5. Find s when p is 75. All right, here's what I know. Look at our phrasing here. P varies directly as s. P varies directly as x. What does that tell me? That tells me that, you know, before it was y varying directly as x, right? So y equals kx. Now it's the perimeter varies directly as s. P varies directly as s. So I can say P is equal to k times s. Okay. I know some of you out there are like, okay, dodecagon, how many sides does it have? But hold on. Okay. The perimeter is 18 when s is 1.5 inches. Okay, well that gives me enough information right there Like that's an ordered pair, right? The perimeter is 18 when the side length is 1.5. So I'm going to do a little prep work here. My perimeter is 18 when my side is 1.5. So to get that, my K value, I'm going to take 18. I'm going to divide it by 1.5, and I'm going to get 12, which makes sense. How many sides does a dodecagon have? 12 sides. And any perimeter is equal to the number of sides times its side length. Right? So the perimeter is 12 times x. Now, it says find s. This is my equation. This is my direct vary equation. Now what we're going to do is answer the question. Find s when p is 75. So 75 is equal to 12 times my side length, whatever that is. So I divide by 12 over to the other side. 75 divided by 12 gives us 6 1/4, 6.25. So answering the question, find s when p is 75, 6.25 inches. That's the side length. We didn't really even need to know the perimeter formula. 12 times the side length, as long as it's regular. Okay? Regular meaning all sides equal. All right, so that's direct variation. That should be not new material. That's what we've learned before. Okay? Now we're going to add into it. We're going to talk about joint variation. We had direct variation, now we're going to talk about joint variation. Basically, a joint variation is when two things are varying directly. They're joining together. A joint variation is a relationship among three variables, or four, or five, that can be written in the form y is equal to kxz. Notice how if I say varying directly as x and varying directly as z, you would say y is equal to kx, y is equal to kz. So you can kind of combine those, you can join them together and say y is equal to kxz. K being the constant of variation, x and z being our variables, whatever they may be. Okay? Where k is the constant of variation and x and z are the variables. Okay? So this is a joint variation here, y is equal to kxz. And the phrasing we would have is y varies jointly with x and z. Okay, y varies jointly with as x and z, or varying jointly with or varying jointly as x and z. So whatever. What's wrong?
Is that for like a three-dimensional graph?
Well, now we're not really talking about graphing. It's more situation.
Yeah, but if you were to graph that, would that be?
Yeah, because you'll have an x, a y, and a z component, so it could be three-dimensional graph. I'm not gonna make you do that, but yeah. So let's take a look here at how it does apply. The volume of a cone varies jointly as the area of the base b and the height h. Okay, the volume of a cone b varies jointly as the area of the base, capital B, and the height h. All right, that right there, I'm not even going to read the rest of the problem just quite yet. That right there tells me enough information I need to know to create my equation with just variables in it. How do I know that? Well, the volume V varies jointly as B and H. Okay? V varies jointly as B and H. So that tells me that V is equal to K times capital B times H. So multiplication in here. Okay, basically we could have also said that the volume varies directly as the base, area of the base, and as varying directly as the height. Okay, you could say varying directly separately, or you could just combine the wording and say varying jointly. All right, now, the next part tells me enough information to solve for K. It's basically giving me a whole set of parameters saying, okay, knowing that this is true now, let's solve for our K value. So doing a little prep work coming off to the side, the volume is 12 pi. The base area of the base is 9 pi. And the height is 4. I've basically put in all of my information and I've left K as my variable because now I can solve for it. So just simplifying it on the right side, 12 pi is equal to 36 pi k. Divide by 36 pi over to the other side. Pi's will cancel. So 12 over 36 is 1/3. Which makes sense because if you remember the volume of a cone formula, its volume is equal to 1/3 the area of the base times the height. That's the volume of a cone formula. 1/3 the area of the base times the height. Or in other words, the area of the base is always going to be a circle, 1/3 pi r squared times height. Okay. This is also the volume of a pyramid as well, 1/3 area of the base times height. All right, now the last part of the question says, find B when the volume is 24 pi and the height is 9. Okay, so now I can say, well, 24 pi is equal to 3 times the area of the base. Right, 1/3 of 9 is 3. Divide by 3 over to the other side. 8 pi is the area of the base. 8 pi feet squared. Feet squared. So somewhere around a little over 24. Questions about that? So we've done varying directly. There's varying jointly. And now what we're going to learn is the new one here called inverse variation. Take a look up here. This is not in your guided notes. The third type of variation describes a situation in which one quantity increases while the other one decreases. So as I increase my x values, my y values are going to decrease infinitely. For example, the table shows the time needed to drive 600 miles decreases as speed increases. Think about it. If I know I'm going to have my 600 miles set, I've got to take a trip 600 miles. It would make sense to us that if I increase my speed, what's going to do to the time it takes to get there? It will decrease. As I increase my speed, my total time that it's going to take to get there will decrease. That is something that is an inverse variation. When I increase some value, the other value will decrease. This is what's known as an inverse variation. An inverse variation. Okay? And it's of the form y is equal to k over x. Type of variation is an inverse variation. An inverse variation is a relationship between two variables, x and y, mathematically written as y is equal to k divided by x. It's no longer k times x. It's y is equal to k divided by x, where k is non-zero, just as long as k is non-zero. For the equation y is equal to k over x, y varies inversely as x. That's our phrasing there. That's how you know you're going to use inverse variation. Y varies inversely as x. That's the phrasing that you should see within the problem to know that you're going to use this equation rather than the direct variation. Let's take a look. Given y varies inversely as x, when y is 4, when x is 5, write and graph. This is the same thing we did with direct variation. Shouldn't be too difficult, right? So let's say inverse variation. This obviously tells us what equation we're going to use. Y varies inversely as x. Y is equal to k divided by x. And y is 4 when x is 5. Okay, now that next sentence next phrase gives me enough information to find k. 4 is equal to k over 5. So what's my k value? 20, right? 20 is my k value. Okay? Because I multiply 5 over to the other side. So my final equation is y is equal to 20 divided by x. Now, this is the first time that we've had x in the denominator. You may not have realized it, but this is the first time where you have x in the denominator. Not in the numerator, but in the denominator. Okay, so basically, this is our whole next chapter in a nutshell. What happens when you put x within a denominator? And what are the implications of that? Does it matter what you put on top? Does it matter if you make this an entire polynomial in the denominator? What happens when you put x within the denominator of a fraction? Well, we don't know. We've never had anything like this. So what do you do when you don't know what it's going to look like? let's just make a table of values. Now I'm going to make a big table of values, and I'm going to strategically pick x values. Okay, I'm going to pick x values that are going to divide 20 nicely. So say negative 10, 20 divided by negative 10, that's good. 20 divided by 9, no. 8, no. 7, no. 6, no. 5, negative 5, that's going to work out nicely. 20 divided by negative 4, that's going to work out nicely. 20 divided by negative 3, no. 20 divided by negative 2, yeah, that's going to work out nicely. Well, we should pick 0, because it's always good to see what's happening at 0. And then let's pick all the positive versions of those numbers. 2, 4, 5, and 10. Because this is a pretty easy operation. Okay, what's 20 divided by negative 10? Negative 2. 20 divided by negative 5? Negative 4. 20 divided by negative 4? Negative 5. 20 divided by negative 10, 2. Negative 10, let's count on the bag there. 20 divided by 0? No. No. Undefined. It's undefined. You cannot divide by 0. It is undefined. That's going to be weird. Watch me. 20 divided by 2 is 10. 20 divided by 4 is 5. 20 divided by 5 is 4. 20 divided by 10 is 2. Okay, so let's see what's going to happen here. I've got negative 10, comma, negative 2. I've got negative 5, comma, negative 4. I've got negative 4, comma, negative 5. I've got negative 2, comma, negative 10. And then it jumps. 2, 10, 4, 5, 5, 4, 10, 2. This is what this graph is going to look like.
Oh, that's
That's what we have. That's what this graph is going to look like. This is what's called a rational function. Got 2 tails to it. Got 2 pieces to it. There's actually a horizontal and a vertical asymptote to it. Okay, it's going to lie tangent to those asymptotes on either side, up and down, left and right. Okay? That's what we're going to be working with all chapter. And how does that work? How do we add, subtract, multiply, divide it? How do we transform these things? How do we shift these things? All sorts of everything that we could possibly do. What's that? Nah, this is fun. I like this. One of my favorite ones.
You say that every day.
You can use algebra to rewrite the functions into, we're just scratching the surface right there. That's kind of like a little bit of like a foreshadow. You can use algebra to rewrite variation functions in terms of k. What's unique about variation functions is that you can always solve them for k. So notice that in a direct variation, k is equal to y divided by x. In an inverse variation, if you solve for k, k is equal to x times y. Okay? What we can see is either a constant ratio or a constant product, depending on if it's an inverse or direct variation. So if I give you let me go back. Yeah, we're good. Notice that if I give you a table of values, you can tell whether that's going to be a direct or inverse variation just by taking either y times x or y divided by x. Okay, so what we're going to do here is we're just going to add on another couple layers to this table. And what we're going to do is k is equal to x times y. This would be checking if it's an inverse variation. And then k is equal to, what was it? It was y divided by x. Y divided by x, that's checking if it's a direct variation. Okay. Because it could be an inverse, could be a direct, could be neither. I don't know. Let's check it though. So let's check x times y. 6.5 times 8. Oh, that's 6.8. 6.5 times 8 is 52. 4 times 13, 52. 1/2 of 104 is indeed 52. You know, we don't even need to check direct variation because we see that this is an inverse, but I'm going to show you what happens if I try to check for direct variation. We take y divided by x, 8 divided by 6.5 gets me 1.23. 4 divided by 13 does not give me 1.23, gives me 0.307. And then 0.5 divided by 104 gives me 0.005. So do you see how there is a constant of variation? The constant variation is 52. So we know that this would be an inverse variation. It could be direct, could be inverse, could be neither. Okay. So let's check the next one. Again, what you're going to do here is you're going to check for k is equal to y times x or x times y, which that's an inverse variation. The direct variation would have been the k value equaling y divided by x. And now we check each one. So 30 times 5 is 150. 48 times 8 is not going to be 150. 384. So I don't even need to check this. That's not going to be, doesn't matter. And then we check y over x, 30 over 5, that's 6. 48 over 8, 72 over 12. Whoa, should have made it like 7 or something. So I know this is a direct variation. The last type of variation that we're going to look at, this isn't even really a new variation. But what I can do is I can combine everything that we've learned today and call it a combined variation. A combined variation is basically a relationship that contains both direct, inverse, and it could contain joint variation as well. Okay, quantities that vary directly appear in the numerator, quantities appear, that vary inversely appear in the denominator. Here's what I mean. If I say y varies directly with x, just that phrase alone tells me y is equal to k times x. If I add on to it and inversely as, I don't know, b, y varies directly with x and inversely as b. Anything varying inversely will go into the denominator. K always appears in the numerator. Anything directly always appears in the numerator. Anything inverse appears in the denominator. So let's take a look here. The volume V of a gas varies inversely as the pressure P and directly as the temperature T. A certain gas has a volume of 10 liters and a temperature of 300 Kelvin and a pressure of 1.5 atmospheres. The gas is heated at 400 Kelvin and has a pressure of 1 atmosphere. What's its volume? Okay, we're going to take this piece by piece. The first piece that we're going to take is this here. That's going to tell us the exact equation, just variables that we're going to write. Okay, the volume, V, varies inversely as P. Okay, I can start there. Volume varies inversely as P. K over P, right? And directly as T. So it's varying both inversely and directly. You know what a lot of people try to do on this test, or whatever we have this assessment? You try to split it up and create like two equations. No. It's a combined variation. You combine it into one equation. So if it's varying directly with T, T just goes on top. You would say V is equal to K times T. So it's V is equal to K times T divided by P. All right, now my next set of information is going to give me the prep work. A certain gas has a volume of 10. Okay, volume 10. I'm not going to know K just quite yet. a temperature of 300 Kelvin, and a pressure of 1.5. Let's figure out what our constant's going to be. So I can take 300 divided by 1.5. Whoa, that's 33. 300 divided by 1.5. And I'm going to get 200. So 10 is equal to 200K. Divide by 200. 10 over 200 is going to give me 0.05. 0.05 K. That gave me enough information to write out the equation where I no longer need to substitute K as my constant. So V is equal to 0.05 T divided by P. 0.05 T divided by P. Now it says, okay, if the gas is heated to 400 Kelvin and at a pressure of 1 atmosphere, what's its volume? Well, 0.05 times 400 divided by 1, 20. The volume would be 20 liters. Questions about that? Yeah.
For the last one, like the determinant of direct or inverse, I mix these up.
Or this?
Yeah. Because our inverse is x times y.
Yeah.
So then you go down to the other inverse one and you divide it.
You go down to the other.
And the second one, if you
Yeah. Okay, so take a look at here. This is solving for K. Solving for K. We just kind of manipulated our equation so that we could solve for K. I'm still going back to the original, direct variation is y equals K times X. Right? To solve for K, we just divided that X over to the other side. Inverse variation is y is equal to K divided by X. What we were doing in those tables, we had just solved for K, so we could pretty easily tell if there was a constant or not. Does that make sense? Yeah. Kind of flipped it around. All right, let me turn off the video here.